Hey everybody! So we're about to move into the next unit on our study of mechanics, and as we discussed in the first unit that we did, mechanics is the study of motion. And the first unit that we did, dealing with mechanics, we spent most of our time talking about kinematics. Kinematics is a branch of mechanics where we are describing motion without necessarily explaining it. So we talked about that there are four questions that we want to answer when we are describing motion. Where is the object? What is it doing? What is it going to do next? And when are all these things happening? When we talked about that we use displacement, velocity, acceleration, and time to describe those things. But again, we're only describing. Kinematics is only about describing something, not explaining it. And we have these W questions here that we use to describe something, but we're missing one big W question. And that W question is, why? Why do all these things happen? Why is an object 10 meters from the reference point? Why is it traveling at 15 meters per second to the north? Why is it accelerating at 9.81 meters per second squared? All those questions don't get covered in kinematics, but they will get covered in the next section of our unit, and that deals with dynamics. Dynamics takes us into Newton's laws, and as you can see here, this is the hero of our story here. This is Newton. So the next section, we deal with forces in Newton's laws, or sometimes a branch of mechanics referred to as dynamics. So before we get straight into that, let's talk a little bit about our man Newton here. So obviously, I'm assuming most of you have heard of Newton before, and if you haven't, I'm not really sure what your teachers have been teaching you up until that time. But just a quick bio as far as Newton is concerned. Okay, first, he was born on Christmas in 1642. So if any of you are familiar with Neil deGrasse Tyson, on Christmas he likes to give Christians a hard time about Newton's birthday being on December 25th as well as Jesus' birthday, but that's neither here nor there. So anyway, in the little description here, and I realize I got this from Wikipedia, but it's all pretty legit. Okay? Newton's English, all right, and recognized as one of the most influential scientists of all time. A key figure in the scientific revolution. So if you look at his lifespan, right, 1642 to 1726, we're talking here, you know, the Renaissance, the Enlightenment in Europe, but it's a little bit later, right? It's not like the 1500s and the 1600s, and that's going to be important in a second. The most important work that Newton did, at least from our standpoint as it relates to this class, is he published a book called the Philosophiae Naturalis Principia Mathematica, which is Latin, because that's what most scholarly writing at the time was written in, published in 1687. So you'll notice he's about 45 years old at the time, if I did my math right. Yep, 45. Okay. And it says here, it laid the foundations for classical mechanics. In this picture, right, here he is. He's holding a copy of his book, The Principia, which was really a watershed moment in the development of ideas that govern the laws of motion in the universe. So, let's talk a little bit about how Newton got there. You'll notice here down at the bottom it says that he went to Trinity College in Cambridge, which has turned into the University of Cambridge, famous university in England. So 1667 to 1668. Oop, that's ugly, but that's okay. So we're talking, you know, early 20s, right? He goes to college just like a normal student would. But while he's at college, he gets sent home because, you know, social implications of things going on. The plague is happening in England at the time. And any large congregations of people, they fear or they know that will, you know, infect each other with the plague, so they close the university for a while. Newton returns home to his farm, his family's farm, and he's not really into farming as far as I'm aware, And so he just kind of sits around the farm and, I don't know, watches other people work, I guess, and makes observations and looks at old studies of things that have been done up until this point. And then one day, allegedly, an apple falls from a tree, and that makes all of it click for him. I don't know if there was an apple. I don't know if it fell from a tree. I don't know if it hit him on the head. I wasn't there. But something makes him start putting the pieces together and answering questions that people had had for a really long time. Data that didn't seem to make sense of previous scientists could now be explained by what Newton was putting together. So one of the famous quotes that is attributed to Newton is, "If I've seen further than others, it's by standing on the shoulders of giants." Newton realizes that his scientific work is not done in isolation. It is dependent on a bunch of things that people have done before him. And that's kind of the case of how science works all the time. Very rarely does a scientist, or anybody for that matter, make a discovery without using something that other people have done. Now, that being the case, right, it may be significant, it may be insignificant what the previous work does, but regardless, Newton has taken a bunch of things that have been previously measured, have been previously determined, and makes sense out of all of it, or puts some mathematics behind it that really makes it all the pieces of the puzzle fit. And one of the guys, one of the giants that Newton was standing on the shoulders of is this guy. That's Galileo. So, here's Galileo's bio. Again, I realize it's from Wikipedia, but whatever, okay? So, if you look at Galileo's lifespan, he lived before Newton did, 1564 to 1642. If you're perceptive, you'll notice that Galileo died in 1642 and Newton was born in 1642. Coincidence? Maybe. Who knows? But if you look up here, you'll see that one of the things that Newton or Galileo is referred to is the father of modern physics. The stuff we're going to look at in the dynamics chapter are called Newton's laws, and he published them. But a lot of the work that was done that Newton based his work off of was done by Galileo earlier than him. So let's not lose sight of what Galileo did, because he made an important contribution here. All right? So, returning to Newton just for a second here, something else that Newton is known for, it says here that he also shares credit with Gottfried Leibniz for the development of calculus. One of the things that Newton was working on, not necessarily with the motion things, he was having some problems explaining observations and explaining what people had measured before, and one of the reasons was that the math was limited. So he basically made up math that answered that solved his problems, which we now today refer to as calculus. And like I said, there's another guy, Leibniz, who is also sort of credited with the development of calculus. As far as I know, they weren't working together. I think there's I don't know if there's like a turf war in math, as to who discovered calculus, whether it was Leibniz or whether it was Newton, I don't know. But anyway, Newton also made some significant discoveries in the field of optics, not explaining light, but making some observations about color and about prisms and things like that. He would later go on to serve as a politician later in his life, and eventually had kind of a nervous breakdown a little bit later on in his life, because earlier in his life he was involved in alchemy, which, if you're not familiar with, is the science, quote unquote, of trying to turn certain metal or rocks into precious metals like gold. That was a pretty legit scientific venture at the time. They didn't know about atoms or protons or anything like that, but one of the things he experimented with was mercury, and that can cause brain damage. So anyway, that was Newton, but we're going to focus mostly on the Principia, like I said, and the ideas that he put forth in that Principia. So let's start then, not with Newton, but with Aristotle, way back. Here you can see this is a selection from your book. It's on page 44. But it talks about how this scientific development, like I said, doesn't happen in isolation. One thing builds on the next. And so this question of why do things happen? Why does this object move? Why does that object not move? Or like we discussed, this field of physics or mechanics that we sometimes refer to as dynamics starts way back with Aristotle. He asks the question, why does that rock sit there? Why, when I roll something along the floor, does it stop when it gets to the other side of the room? Why do things fall from the sky and end up on the ground? And I'm not going to read this to you, but one of the things that Aristotle proposed is that there is something called the natural state of an object. That there is a natural state that something exists in, and that if we put it in an unnatural state, it will do everything it can to return to its natural state. Now you might think, okay, well, we'll see here in a second, based on what you learned back in, 7th grade, you are more sophisticated in your analysis of a situation than a great mind like Aristotle was. But, experience, right? You have a lot more experience. And here was the problem. So, trying to explain motion, one of the things that Aristotle observed about motion, is that everything comes to a rest. Something that's moving will ultimately stop moving. Why? Well, that was every observation that anybody had ever made about motion. Anything on Earth that is moving will ultimately come to rest. Sometimes it happens quickly, sometimes it happens more slowly, but it still happens. And things that aren't moving just don't start moving on their own. So Aristotle proposed that rest must be the natural state of an object. Why? Well, things that are at rest don't start moving. Things that are moving eventually end up at rest, so there must be something special about being at rest. And this was the prevailing thought that Aristotle put forth. Didn't really have experimentation, just sort of used logic and was like, well, this must be the case. But Galileo comes along and realizes through his own thought experiment that that's not the case. There is no such thing as a natural state, or the fact that the natural state of object is rest is inaccurate. Newton takes that idea. Sorry about that, forgot the bell was ringing. Newton takes that idea and puts it together in what we refer to now as Newton's first law. So Newton's first law is summarized by these two statements at the top. Objects don't start or stop moving on their own. That's contrary to what Aristotle thought. Aristotle knew that objects wouldn't start moving on their own, but according to his experience, things stopped moving on their own, right? Something rolling across the floor just ultimately stops eventually, right? Why? According to Aristotle, that's the natural state of things. But Galileo and then later Newton realized that is not the case. What is actually going on is that objects' motion does not change on its own, regardless of what that motion is. So, the key points of Newton's first law, you've probably heard this before, an object at rest remains at rest as long as there is no net force acting on it. Aristotle knew that. The other part is the tricky part. An object moving with a constant velocity continues to move with the same speed and in the same direction as long as no net force acts on it. That's the harder part to figure out. These two things together are referred to as Newton's first law. An object's motion does not change on its own. Newton's first law deals with things staying the same or not changing. It's not that there is a natural state of something at rest. The natural state of something is to stay the same. do whatever it is currently doing. We refer to this idea as inertia. All right? You've probably heard that term before, at least I hope you have. And as it says here, right, the tendency of an object to resist any change in its motion. If it's sitting still, it will stay sitting still. If it's already moving, it will continue moving. That is contrary to pretty much every observation that you have made about motion in your life, or at least a direct observation. But if we can isolate an object from the net forces, or the things that cause the change, which we'll talk about in a second, we will see that things continue doing whatever they are currently doing. This is what space programs use to send rocket ships to the moon or to Mars or wherever we want to get to Pluto. Once we get it out of the forces that affect it here on Earth, gravity, friction, air resistance, if we start an object moving, it will just keep going. That's that idea of inertia. More specifically, it will keep going in a straight line with a constant velocity. Right? We refer to that as our law of inertia. All right? So, Newton's first law deals with things staying the same. That then brings us to Newton's second law. Newton's second law of motion, it tells, it tells exactly how a force changes an object's motion. We have discussed changes in an object's motion previously. We refer to changes in an object's motion as acceleration. Right? Oh, that's ugly. Acceleration. Acceleration is how much does the motion of an object change. Newton's second law tells exactly how that happens. And how much an object's motion changes depends on three things: force, mass, and then the resulting acceleration. This equation tells how force and mass, or shows how force and mass affect the acceleration of an object. And if you know anything about math, right, okay, so here's acceleration, here's force. Force is on the top of that fraction. So if we make force bigger, but keep the mass the same, acceleration has to get bigger to keep the two sides of the equation equal. Acceleration is proportional to the force. However, mass being on the bottom of that fraction, if we make the mass bigger while keeping the force the same, if the bottom of a fraction gets bigger, the answer, quote unquote, to that fraction has to get smaller. So acceleration is inversely proportional to the mass. This equation summarizes those relationships between force and mass and how they affect acceleration, although usually we see Newton's second law written in this form: F equals ma. It might not be the most famous equation out there in science, but it's definitely one of the most important, and one of the most important that we will use, especially over the next couple of weeks. And notice these two equations here, right? They're just two forms of the same equation. You multiply both sides of this equation by m, you get F equals ma. All right? Visually representing that relationship. Acceleration is proportional to force. Here, constant mass. So we got to keep the mass the same if we're going to look at the relationship between force and acceleration. If we are to double the force, right, going from F to 2F, I think most of you could probably see if we pull on something harder, what's going to happen? Well, it's going to go faster. right? More specifically, though, it's not just going to go faster. It's going to increase in velocity twice as fast. So when we say, quote-unquote, it goes faster, that's true, but more accurately, it picks up speed faster. Now, the other part of it, right, acceleration is inversely proportional to the mass. First, you got to keep the force the same. So F here and F here. We're pulling on something exactly the same, with exactly the same amount of force. But if you make it heavier, if you double the mass, you're only going to get half the acceleration, right? Let's say you're pulling a little kid in a wagon, right? And you're moving along at whatever clip. If another kid jumps in the wagon, guess what? You're going to go slower, right? But it's not just you're going to go slower, that acceleration is going to be less, all right? So, Newton's second law deals with acceleration, right? Whereas Newton's first law deals with inertia, right? Inertia, things stay the same. Acceleration, things change. So now Newton has covered, okay, well, why do things stay where they are? And then why do things move? And that's the whole gist of dynamics, all right? So, just some things that come out of that. We will introduce a new unit in this section here called the Newton, all right? Notice, Newton, the unit, starts with a lowercase n. The symbol for Newton is a capital N. Newton the guy, oh, that's Galileo. Newton the guy is a capital N. So if we write the word Newton, if we're talking about the guy Newton, we capitalize the N. If we're talking about the unit Newton, lowercase n. But when we symbolize or when we represent the unit Newton, we use a capital N. I know it's confusing, but you'll deal with it. So, all right. So we take a look here. Newton is a derived unit. It's a combination of base units. And when you see here, you'll see that this combination of base units is equal to the Newton. So anytime we write the capital letter N to represent the unit Newton, we're really representing this combination of base units. It's the base units that go along with mass and acceleration. If we combine those together by multiplying them, we end up with the unit for force. It's really just multiplication, bringing them together. So kilogram is the unit for mass, meters per second squared is the unit for acceleration. If we bring them together, sometimes we'll see it written like this. Or if you're IB, you'll write it like this. All right? This combination we represent with the capital letter N. Okay? And it comes from combining the units for mass and acceleration. But very rarely will you see a situation where there is only one force acting on an object. So, right, in these pictures here, there's only the force that is being supplied by this hand right here, or at least that's what they're representing in this picture. But in reality, there are rarely an occasion where you're only going to have one force acting on something. We can apply Newton's second law to multiple forces, or to what we call the net force. We use the Greek letter sigma to represent the sum. So anytime the Greek letter sigma shows up, it's representing the sum of something. If it shows up in front of an F, right, it's representing the sum of all forces. However, keep in mind, forces are vector quantities. If you push on an object to the left, that's different than pushing on it to the right. Force is a vector quantity. It has direction. So when we write sigma F like this, we're really talking about the sum of the forces, which we call the net force, but in reality, we are talking about the vector sum. or the resultant force, or the resultant vector. In one dimension, that's not a problem. But in two dimensions, we're going to have to get into vector addition using Pythagorean theorem, right? If there's a force this way and there's a force this way, the net force would be this. So keep that in mind. We'll talk about it more on Friday. But the ideas of Newton's second law, the relationships between acceleration, mass, and force, can be applied to more than one force, or the vector sum of the forces. We'll use that a little bit later on to analyze more complex situations. So, to review, Newton's first law. Newton's first law deals with things staying the same. We summarize those ideas with the concept of inertia. Newton's second law deals with things changing, or acceleration. And we use this equation or this equation to summarize the effects that force and mass have on acceleration.